So Tassos here.
Hello.
So hello everybody. This is a first training session on a protein corona modeling tool, which is available by the NanoCommons consortium. NanoCommons is a research e-infrastructure project offering access to high quality nanoinformatics tools and services for nanotechnology, for nanosafety. It is targeted to different stakeholders, including the academia, industry, and regulators. It shall be user-led, offering and developing services that are needed by the user community of nanotechnology and nanosafety, and also by related fields. We built on three main pillars, which are joint research activities, networking activities. There is also transnational access services. One of our research activities is into the direction of modeling protein corona and also other biomolecule corona around nanoparticles. And there is a specialist group in our consortium at the University College Dublin. It's Dr. Vladimir Lobaskin, and he is going to present now to us a model and also explain to us how it's going to be used. So I will give now the moderation rights to Vladimir, and we are going to display his screen. So Vladimir, you can start. The floor is yours. Thank you very much.
Thank you. So do you see the presentation now? The first slide?
Yes, we see.
Yes.
Okay, thank you. So this Corona modeling tool is something that will be delivered as a part of NanoCommons project activities, deliverable 5.6. So in the deliverable report, we'll give a complete description of the methodology and use case. So here I'm going to present the model and such what the tool will be doing, the methodology behind the calculation, and some indications on how users can actually apply this tool to their problems. So first of all, I start with the short motivation. So we decided that corona is extremely important for predicting nanoparticle activities. So understanding how the nanoparticle that got inside live tissues interacts with biomolecules, with the lipid membranes and the parts of the cell, actually determines its fate and eventual adverse outcomes. So we envision the process as follows. So at first, a bare particle meets some biological fluid. Quite often, it could be lung lining fluid when the particle is inhaled, or where particles ingested or introduced into a bloodstream. Then it will be coated with the biomolecules. Most likely, these are going to be proteins. And then those proteins will change the way, and it has been shown with many experiments and observations that the corona changes the way the particle penetrates into the cell, the way it is transported in the bloodstream, and the way it is taken away by the organism. So the understanding of these interactions is central. So therefore, we thought that we need to quantify these interactions and deliver material-dependent properties so that we could tell the difference between different materials and explain why one material is different from the other in terms of cell uptake and subsequent activity. So in this schematic diagram taken from Ken Dawson's group picture, so you see these main stages of the process. Particle gets enveloped with the proteins, and then those proteins basically mediate its interaction with the cell membrane and cell uptake and further fate. So these are the main things why we want to model the corona. And what we want to achieve here is to establish relationships between the physicochemical properties of the nanoparticle, specifically of the nanoparticle surface, and its later biological activities. So the approach is physics-based. So we start from first principles, more or less, and we construct the nanoparticle interaction with an arbitrary protein or a lipid molecule from the basic interactions. So generally in all atom molecular dynamics, overall interaction energy between two molecules is represented as a sum of pairwise interactions. Sometimes the interactions are not just pairwise, like the torsional or semi-flexible bonds may include several atoms, but most of the time they are pairwise. And it can be split into bonded and non-bonded interactions. So the first approximation that we're going to make is following from this. So bonded interactions will be considered only as internal for the nanoparticle and the protein, and in the following will be neglected. So if we represent the total energy of interaction between a nanoparticle and the protein, so strictly speaking, we need to calculate the sum of interactions between each pair of atoms. So it's, sorry, as shown here. But then part of those interactions, bonded interactions, will be internal, and we assume that they simply will not change during the interaction. So internal bonds within the nanoparticle are not changed, and internal bonds within the protein are not changed. So therefore, we neglect the change of protein conformation. Then we assume a pairwise additivity of the potentials. And then with these two assumptions, we arrive to the following. So we can compact the sum of all pairwise atom-atom interactions into the following sum on the right. It's going to be sum of interactions between certain coarse-grained beads. So we group interactions between the atoms entering, constituting the same amino acid, for example, together to calculate the interaction potential for the entire amino acid with the nanoparticle. So therefore, sum of non-bonded interactions will be represented as sum of interactions of each amino acid with the entire nanoparticle. And then we still calculate a different level two contributions, non-bonded interactions, which will be mostly Lennard-Jones, van der Waals interactions, and electrostatic, which are calculated from charged residues and surface charge of the nanoparticle. Then further on, for non-bonded interactions, we split the interaction even further into surface and core. So we just realize that the interaction of an amino acid with the nanoparticle surface is mediated by water and ions in solution, while interaction between the amino acid and the core of the nanoparticle does not include that mediation. So basically, this will be two substances, continuum substances interacting through third continuum substance, water. So therefore, we calculate the surface interaction with a higher resolution and core interactions with a lower resolution just by integrating the van der Waals forces over the volumes of these interacting elements. So this is a program. Now I'm going to show you the overall scheme. So what the tool is making is calculating several interaction parameters in interaction energies for amino acids and entire protein. So once a user has protein ID from a UniProt, for example, a database, thus we could fetch the entire amino acid sequence for the protein. Then the next step is we check whether the 3D structure of this protein exists in the protein data bank. If yes, we just fetch the structure. If not, we generate it using homology model. Then this creates united atom model. So we first get all atom model of a protein and then condense it. Each amino acid will be represented by a single bead. And then, according to the three contributions that I mentioned, so we will use surface interaction of this amino acids with the nanoparticle, then core interactions of the nanoparticle with the amino acid, and electrostatic. They all contribute to evaluation of total interaction energy at a given orientation and given position of a protein with respect to the nanoparticle. After this, we can further condense it and calculate complete Boltzmann average interaction energy for the entire protein with the nanoparticle. So I'll show you examples at the end. So the outputs of the model are as follows. Absorption energy for individual amino acids, then energy heat map by orientation for the entire protein, and absorption energy for the entire protein. So the model is built as follows. So the first step that I mentioned, starting from all atom representation of a protein, we coarse grain it. That's first coarse graining step, where we represent each amino acid by a single bead, and then it is placed at the alpha carbon, and then we fix the structure. The protein is further considered as a rigid structure. So therefore, the patches, charge patches or hydrophobic patches, or the specific shape and say convexities, aspect ratio are all preserved from crystal structure of the protein. Then, if we don't have known crystal structure for the protein in the data bank, we use homology modeling and ITASR tool to generate a prediction of three-dimensional structure. So these predictions work pretty well. They are not perfect, but produce reasonable structures. And we can further use the structure generated using ITASR for the same calculation. Either way, this first step ends with the creating a 3D protein model with 1 bead per amino acid with a fixed shape and conformation. Then the next step is to calculate interaction of that coarse-grained protein with the nanoparticle. So the core potential is represented by Lifshitz theory and Hammaker procedure, where we integrate interaction of each bead, each amino acid inside the protein, over the core of the nanoparticle. Core is defined as everything that is not surface. So surface, I will define later from the surface interaction potential. We simply integrate the 1 over r to the 6 potential, and the formulas that we derived have a different shape depending on how far the protein is from the surface. It could be standard Hammaker potential for 2 spheres, or it could be Hammaker potential minus the length covered by surface interaction. Then the input values for this procedure are the Hammaker constants, A1 to 3. So it's interaction of amino acid, which is substance 1, with the nanoparticle substance 2 through water, which is substance 3. So the formulas differ in the Lifshitz theory depending on whether the nanoparticle is dielectric or conductive. So the formulas are both given here. And we use the known amino acid refractive indices tuned from solution refractive index measurements. So we can calculate those Hammaker constants for specific material, for example, gold to amino acid through water, using those data. Then the surface interaction now is the most detailed part of this, simply because this should take into account occasional hydration effects, and they appear to be pretty important, and orientation of amino acid. So it is done using atomistic simulation. For the purpose of this tool, we use already pre-calculated potentials of mean force. As of now, this calculation is not included in the tool, but will be included later on. So procedure is described here. It is a metadynamics. Basically, what is done, the amino acid is moved up and down, the distance changed from the surface, and then the interaction potentials are fitted so that we calculate average interaction free energy at different distances. So finally, we arrive to a set of curve. For each amino acid, we generate angle average curve of free energy versus distance. And this curve is then calculated with the given interaction cutoff and is included in the overall energy calculation. So then the calculation is done for flat surface, and within this tool, we correct it for given nanoparticle radius. Radius can vary from say 2-3 nanometers to 100 nanometers, and the interaction formula, correction formula, includes the curvature, so that the actual length of the material that is within the reach of the amino acid is less for a curved particle. But the correction is usually not very large. So for smallest nanoparticles, it may be 20-30% less weaker interaction than for a flat surface. Then we do orientational sampling. So now you see, in case for interaction of a protein with the flat surface or a spherical nanoparticle, the protein we're starting from the protein data bank orientation, predefined orientation, and then rotate the protein around to about two axes. One is perpendicular to the surface, and another is parallel to the surface. So we sample all possible orientations of the protein. Then in each orientation, we move the protein with respect to the surface, so that this distance, d(COM), center of mass, is changed, and calculate the Boltzmann average, ensemble average over those distances. So energy is averaged. Then we calculate, this procedure gives us a single value of energy for each pair of angles, azimuthal and polar rotation angles. And then finally, we calculate overall absorption energy using this Boltzmann weighted average again. So the first line here generates heat map, single energy for each orientation, averaged over distances. And the second line gives the mean absorption energy for the entire protein, a single value. So now I give you examples. So we will present it together with the tool. We did a calculation for gold nanoparticle. We decided to do it for gold because the gold has the most extensive corona data set, probably the most advanced, and many other computational tools, including the jackpot tools, tuned for gold. So on this slide, what you see is a set of Hamaker constants for the gold and individual amino acids. So you see the numbers, and these are given in kilojoules per mole. Then the next thing, so the Hamaker constants are used in the core potential. Now for the surface potential, this set of curves represents the interactions, potentials of mean force obtained in all atom molecular dynamics simulations with the metadynamics. So you see, depending on the type of amino acid, they may prefer to have a water layer between themselves and the surface. Some of them show just really strong attraction, and some of them show a barrier in between. but also the depth varies depending on the size and the shape of the amino acid. So these potentials of mean force are integrated over distance using this relationship, so that we calculate average absorption energy per amino acid, and this can work as a very informative descriptor of the bio-nano interface and use it to fingerprint the materials. So you see, depending on the size and charge of amino acids, they will be attracted weaker or stronger. So the strongest attraction in this table is for arginine, and the weakest the glycine. Then further on, I said we calculate absorption energy for each orientation and for each nanoparticle shape and size. And here you see two examples of energy heat maps. So the depth can be pretty low, to minus 60 kBT in this case. And this heat map gives you an idea of preferred orientations. For example, one preferred orientation is about 110 theta in polar angle and 140 in azimuthal angle rotation. And this is done for 5 nanometer large gold nanoparticle. For 100 nanometer large nanoparticles, the preferred orientations are different. So this minimum here is already present for small size, but it becomes dominating on the large size. It's 114 in the polar angle and about 190 in the azimuthal angle. So these heat maps can be used to predict the preferred orientation of the specific protein on that specific nanoparticle. Then we also calculate the dependence on size. This will not be reported by the tool, but it can be compiled later on. So the user does a calculation for a different nanoparticle radii. And you see here the dependence on the nanoparticle zeta potential. So zeta potential can be set by specific coating. If you use carboxylic citric acid coating, it can change the surface charge, and you see how the overall interaction energy depends on the charge. So this is also one of the things that the tool delivers. And a final example here is the protein ranking. So in this table, you see the 10 different proteins are ranked by their absorption energy in the ascending order. So you see of these proteins, the strongest binding one is hydrophobic lung surfactant protein SPD, which gives minus 214 kBT, absorbing on a neutral gold nanoparticle, and the weakest binding is ubiquitin. But you see the ranking can be different from that on the smaller nanoparticle. So in principle, these tables already exist for several hundreds of proteins, and if the user wants to find something specific, it may be already calculated and reported in the tables in the database, or if it's a completely new protein, that could be ranked, and what can be looked up is the relative rank of that specific protein with respect to some other existing one. So finally, to wrap up, for the tool, what is needed from the user is to specify, to pick a material first. It could be gold, titanium dioxide, or silicon dioxide, quartz or amorphous at this point. To give nanoparticle radius, nanoparticle zeta potential, solution temperature, solution ionic strength to calculate the screening, and give protein uniprot ID. Then the output of the tool will be mean absorption energy for 20 different amino acids, then absorption energy heat map for the protein in the form of a table, say for the different orientation angles, and mean absorption energy for the entire protein. So that's it. If you have any questions, please ask away.
Thank you very much, Vladimir, for this very clear and also concise overview on what the tool can do. I would like to invite for questions if there are from the audience.
Okay, so hello, my name is Mark Geppert. I'm also from the University of Salzburg, working together with Martin. I have a question. So this is only possible for smooth nanoparticles. With what is if the surface is not smooth of the nanoparticle?
Okay, then we need to have an idea what the surface is like. So right now there are several things in progress. For example, we are preparing the same thing for carbon black, which is a porous material and not really even. But basically, what we need to know what information is available about the surface. Then we will try to model it.
So, for example, when we have like a porous surface or just a non-smooth surface, we can like do calculations from nitrate absorption or so. So we have surface data.
Yeah. Okay. So I would say one simple thing. It's not integrated in the tool as of now, but it can be done. For example, if you have a porous silica, then we can introduce a correction for the porosity and for reduced density. That's okay. Probably the only thing we can do relatively quickly. But for the rest, it's a separate challenge to model the surface.
Yeah, I understand, but it's definitely interesting. Could you please go back one slide, the summary slide? Thank you. Solution temperature means the temperature of the medium.
Yes, so it's
okay.
Well, basically it's either room temperature or body temperature.
Okay. Now I was just thinking something different.
There are two options. So it may affect the results slightly. Yeah.
May I eventually ask something? So, Vladimir, is there any influence or impact of also protein-protein interactions as they are accumulating more and more on the particle surface? Is this somehow possible to integrate this kind of consideration? I mean, it could make a difference whether a particle is somehow covered by 5% of its surface with proteins, whereas compared to 100%, or even then having a multi-layer or something like that. How is this?
Yes, well, for the absorption energy, this makes no difference. The absorption energy calculation is the same, but of course that could change the corona content. And what we have also developed, but it's not yet integrated into the nanocommons knowledge base, is a further coarse grain model where we say model kinetics of corona formation and protein absorption. So that is a separate thing. It's not yet automated, but it can be done. We know how to do this, and we have done this already for several materials. Competitive absorption, and their protein-protein interactions are included.
I would ask in a similar direction, not regarding protein-protein interactions, but regarding interactions of protein with other surface coatings. So how can we deal with like if we have gold nanoparticles with or silicon dioxide or whatever with a surface coating of maybe small organic molecules or so, which are also maybe like in the dynamic process with the solution?
Okay, technically it can be done. As of now, we it's not exactly coating, but it's a functionalization of carbon nanotubes, differently functionalized. But say the procedure is essentially the same. We didn't do it for like solid materials like gold or silica, but the procedure as I described is the same. Simply the difference is that the material surface will be modified by those small organic molecules, and then potential Obmin force will be calculated. So as I said, we did it as of now. We did it only for carbon nanotubes with the functional light surfaces, but not for gold or titanium or silica. But it can be done.
Okay, and maybe this question is a bit like directing into another topic, but I think if you can model protein corona, it should be also possible to model just corona formation due to individual amino acids or other organic molecules. Should be possible, I guess, with the model.
Okay, so technically yes, and we know how to do this. What exists right now, we are finalizing the model of lung lining fluid, where we have, for example, lipids and cholesterol and proteins present at the same time. So this is another example. But say another thing that is also done now, developed in my lab, is a interaction of nanoparticle with the coated surface, where you have a brush, like a peg brush, for example, on the surface. That is a more challenging thing, and probably it will not be included as a tool, but it can be done. It requires much more work. So if the surface is of a complex structure, specified complex structure, it would need additional modeling for the surface. But say when you are asking about the other molecules, once molecules are parameterized, we have parameterization for certain sugars as well, lipids, pegs with the surfaces. We can do this.
Okay, this is interesting because we are doing lots of protein nanoparticle interaction studies, and we have like the methodology to measure this. We can quantify proteins via different tools, but for smaller organic compounds, it's sometimes difficult. So if there's an approach to like with some calculations, it's definitely interesting for us. Thank you.
Yes, but in principle, one example I can give our partners with whom we collaborate, they tried to understand how the proteins absorb on the surfaces, and they prepare a solution of peptides. So basically, they cut the protein into smaller peptides and watch absorption of those peptides on the surface. This we can model as well.
So would you say, Vladimir, that digesting a protein being conjugated to a nanoparticle would then not be successful because the absorption energies would eventually not be lower, right? So the peptides would be attached in a eventually quite similar manner as the protein, or digesting with a protease, for example.
Okay, I would say overall energetics could be. I'm only guessing. We never tried this. It could be higher simply because if a protein is folded, it can only get in contact with the nanoparticle with the limited number of residues. But when you cut it into pieces, the contact area, overall contact area, may be much greater. So I would imagine that energetically that will be kind of more favorable, probably. Say the energy gain will be greater in that case for digested proteins, and also for unfolded proteins.
Yeah, unfolding, protein unfolding is a good word also, which interests us a lot. Are these absorption energy values that you determine somehow related to energy values that are required for unfolding of proteins?
So I'd say it's probably the numbers we give are the lowest, lower bounds for that energy. Any unfolding or digestion would lead to higher energies, but that has to be modeled separately, because we need to know what kind of degrees of freedom or what kind of principal components in protein unfolding generally exist.
Okay, thank you very much. Are there any other questions from the audience? If not, I thank you very much, Vladimir, for this very clear and comprehensive overview on this topic. Maybe you can just, as the very last point, mention once again, how do people get access to the tool?
So the access and interface is now in progress. So as of now, I don't know the final shape of it. So between UCD and Biomax, but the idea more or less is as follows: the full tool in the final shape will do the following, how it's shown on these diagrams. Just a second, I browse back. Yeah, so a web interface would require entering a protein ID from the user, and then the solution conditions, picking the material from the list. So as of now, arbitrary material will not work, but it will work for those materials where we have potential submin force already. And then zeta potential and ionic strength for the nanomaterial and radius. Then everything else, like absorption energies for amino acids, orientation, heat map, and overall energy will be calculated and returned to the user.
Okay, and I guess we can announce also at this stage that the NanoCommons web page is going to link to the relevant location in the internet where this tool can be accessed by the nanosafety community. And the web page of NanoCommons is going to be www.nanocommons.eu, so if people are interested in using that. Thanks again for Vladimir and for all the other people for this very interesting webinar.